Oh, I wanted we to do this one. Should be. You were just getting the X. Uh-oh. Is that Y minus 4? That sounds bad. We only want them to be positive, I think. What did you get? Positive 4. Did you make a sign mistake? Well, I'm going to do it on the board now anyways. I think you just made a sign mistake. Right, Prue, can you read the question to me? What's the atom?
The atom.
Yeah. MP. 237. Thank you. Protons? 93. Now this decays, what does it say?
There's a BI.
A B?
BI.
A BI? Oh, BI, yeah. Like this?
Yes.
Yeah.
283.
Okay, plus alpha, X alphas plus Y betas. Okay, so Louise, did you have this?
Yeah.
Yeah, okay. So we can say 209 plus 4x plus 0y must equal 237. And also we can say 83 plus 2x minus 1y must equal 93. So that means we have 4x equals 28, and we have 2x minus y equals 10. Therefore, x equals 28 divided by 4, 7. And if I put that in here, I get y would equal 14 minus 10, so then y equals 4. Yeah? So here what happens is the NP will turn into Bi and make 7 alpha particles and then 4 beta particles. Yeah. This is the decay. What was your mistake, Abraham? Was a sign mistake just, yeah. Here with the minus. Yeah. Make sure you try some of these at home so you know how to do them. Yeah? You have your maths project finished, so you can do them tonight. Yeah? Okay. Hey, oh, that's okay. We were just reviewing some homework from yesterday. Yeah. Okay. Now we'll continue, so let's see. Okay, so just a quick check from last time. What were the 3 types of radiation we did last time? Alpha, beta, and gamma, yeah. Okay. Alright. So what we're going to look at now, which we didn't look at the last time. Last time we were just really talking about the 3 different types of radiation, alpha, beta, and gamma. This time we're going to look more at how those values change. Do you remember last time I said the process is limited? It only goes for some time, then it stops. And we'll also have a look at some equations as well that have time in them. Because we didn't talk about time at all in the last class. Okay. And so the example we looked at last time was uranium. And we know that this is radioactive. So it will release alpha, beta, and gamma radiation. And we're going to have a look now in more detail about that. So something like uranium-239 will decay, and we get our energy out by alpha, beta, and gamma. So what is alpha radiation? What one is alpha? Helium, yeah. 2 protons, 2 neutrons. And beta? An electron, yeah. And gamma? Wait, yeah. So you remember all 3 now, yeah. And who? The beta. Something strange happens with beta as well. Is one electron and something else happens. Do you remember? Something strange with the proton and the neutron. Yeah? That's it, yeah. Do you remember that with the beta? When the electron comes out, one of the neutrons turns into a proton with the beta. You remember that, yeah? Yeah. Okay. But we've not talked about how we can detect this radiation. So we haven't actually said what the radiation looks like. So the first thing, there's no color. So you can't see radiation. So I think maybe these 4 features you should write down, something that you could get in the exam. Something like, why is radiation difficult to detect? So firstly, it's colorless. You can't see it. You just need these points here. It's enough. Yeah. Next, odorless. What does odorless mean? Nope. Do we use odorless? Any ideas? Something what, yeah? No? Abraham? No, odorless? Okay. Odorless means no smell. You can't smell it. So odorless, no smell. This is not like in chemistry, is it? In chemistry, a lot of chemicals have a smell. Yeah. Sometimes a very bad smell. So you can definitely know if something's going on. Tasteless. So what does this mean? Yeah? No taste, yeah? You definitely don't want to do this. Why not? Very, very bad. Yeah. So tasteless, no taste. You can't taste it. Okay. And lastly, chemically inert. And I don't know if you know this from chemistry. Do you have any ideas about what I mean here? Yeah, that's it. Yeah, it doesn't react with other chemicals. So you couldn't use pH strips. You used pH strips with Lorraine, didn't you? So they change color when you dip them into something. You can see the pH level. You don't have anything like that for radioactive materials. Just for what did you use in chemistry for the pH? Hydroxide acid. Yeah, so hydroxide acid will turn the pH strip a different color. You don't have anything like that for radioactive materials. They won't react with anything. Okay, so make sure you got those four: colourless, odourless, tasteless, and chemically inert. So it's important that we know how to detect radiation, because as we said last time, it's something very dangerous. So we do need some way to find it and measure it. Can I go to the next page, Louise, or not? Yeah? I really just need these four here. You got them? Yeah? Okay. So, just like in physics, chemistry, or biology, when you want to measure something, you need to say exactly what you're measuring and what units you're using. So we're going to use something called activity. Activity is the rate at which unstable nuclei decay. So in other words, it's how quickly our atoms disappear. So for example, with our uranium, when there's alpha radiation, how many protons leave the atom? 2. And how many neutrons? No, 2, yeah. So the activity is, like a speed, how quickly things are being lost. Can anybody give me other words for decay? Other synonyms for decay? To mean for something to go away, disappear. Well, disappear, yes, that's true. Something else, maybe? Say again? No, not bad, but not this. Anything else? No? Begins with a D as well. I think you know this one. Destroyed. Yeah. And then disintegrate. So we have 2 other words here we can use. It's good if you write them down. Are destroyed or disintegrated. So this is one of the definitions you could be asked for. It's not a big definition. Okay, you got that? Yeah? Okay. Now, we need to talk about the unit for this. And the unit, this is a new unit for you. Becquerel, or just BQ. So you haven't seen this before. It's an SI unit. And the definition is, so you need the definition here, 1 BQ is 1 destruction or disintegration of a nucleus per second. So 1 BQ means you lose 1 atom per second. So 1 nucleus is destroyed every second is 1 BQ. Okay, so just the definition is most important here. Usually this number is quite large, so it'd be very common to see kilo BQ or mega BQ. Okay. Can I go on, Louise? Yep. Okay. So just to be clear about the letters I'm using here, A I'll use for activity, and the units are BQ. So for example, A equals 5 kilo BQ. And N represents number of atoms. So here, N would be, for example, something like 10 to the power of 6, number of atoms. So this should be, N represents the number of atoms, and A represents the activity. So just A is activity and N is number of atoms. That's all you really need to know. And calculating N is not too difficult, because you've actually done this already. Where have you done something like this before, calculating the number of atoms? Where? Yeah? Yeah, PV equals N or T. What section was that called? Materials, yeah. And you saw it somewhere else? Not in my class. Where else should you have seen it? In chemistry, yeah. So you learned how to do this in materials and in chemistry. So for example, I'll give you a minute to think about this. It shouldn't take you more than a minute. 12 grams of carbon, how many atoms are there? Oh, very good, very good. 6 times 10 to the power of 20 something, isn't it? Yeah. I think it's 23. 6.02 times 10 to the 23. What's the name of this number? Avogadro, very good. So Lorraine will be happy you remembered that. So we won't really talk about calculating the N so much because you've actually seen it twice already. What we really care about is things like the activity. Okay. Right. How many of you have seen something like this before? In TV or a movie or anything like this? Yeah. You know, the people walking around in the white suits? Yeah. Radiation. And what sound does this machine make? It makes a sound when they're walking around. Yeah. I have it here for you. My speakers aren't great, but as soon as I play it, I'm sure you'll recognize it. I'm sure you've heard it before. You heard this sound before? You know you've heard it before. Yeah, well, it's for measuring radiation. So when you hear more clicks, it means there's more radiation. Yeah. I always think about this in movies. Yeah. Anyways. That's called Geiger-Muller Counter, or GM counter. Let me go back here. And in fact, it's a very simple machine for measuring radiation. It's not very difficult. So I'm going to show you the diagram of how it works. You should draw this carefully. It's something which you might get in the exam, although they have not asked it in the exam so far. So there's been about 7-8 years of exams, and I haven't seen them ask a question about this. I think the only thing I've seen is a question like, briefly explain how it works. So I don't expect them to ask you for the diagram, but it's good if you have it. It will help you to remember and understand how it works. So this is the diagram here. So up the top there is the tube, which the person is holding. Okay. And you can see that there's a battery going into this tube. So up the top you have the cathode, and in the middle you have the anode. So do you remember what's between the cathode and the anode? What do we call this that goes between them? What is moving between them? Yeah? Electric field, yeah. So there's an electric field in between the cathode and the anode. And then what happens is some radiation, like alpha, beta, or gamma particles come in, and they'll hit the atoms of the gas that's inside the tube. Now the gas is usually something inert, something like, maybe like helium or something like this. And when the radiation hits the atom, it releases an electron. What do you call this in chemistry? Ionization. So the electron will move towards the anode, and basically what will happen is you'll get more current. So this is a lot like ionization in chemistry. You know ionizing a gas? So when the gas is ionized, because there's an electric field, the electron will move in the electric field. So you can see it's actually a very simple machine, isn't it? You just need a tube, 2 pieces of metal, battery, a window, and something like a voltmeter or an ammeter, something to measure the change. But I think it's worth noticing that I didn't say it was a glass window. It's not actually glass. Why do you think we don't use glass? You might have to think back to what we were doing in the last class about the alpha and the beta. Oh, very good, yeah. The glass would possibly stop the alpha. Because remember, what did I say you could stop an alpha particle with? Yeah, a bit of paper would do it. So this mica material is see-through, like glass, but it's not as thick or dense as glass, which means it's very, very, very easy to break. Okay, so if you drop this, you probably broke it. The window is very fragile, it'll easily break. Okay, so I'll just give you a minute or two, and try your best to draw that neatly in your notebook. What's most important here is you understand how it works. Okay? Yes. Yeah? Yeah?
Are you trying to measure the alpha and gamma radiation?
Any type of radiation. It'll pick up anything.
And it's important to know about the alpha radiation. Because I was thinking what it would matter with the alpha radiation. I was thinking
Why does it matter?
and before we that will prevent the alpha radiation hitting
Yeah.
not very getting the alpha radiation.
Oh yeah, no, that's what we were saying last time as well. So 3 types, alpha is the least dangerous and gamma is the most
They might
dangerous.
want to know if there is
Oh yeah,
alpha
because what will happen is it won't pass through skin, but if you have a cut or if it gets into your food supply, it'll get into you that way. And if it gets into you, like, it's really game over then. Yeah. Alpha's not the one to worry about so much unless it like contaminates something. Oh yeah, or it contaminates a water supply or something like that, yeah. Yes. You got that drawing? Maybe. Beautiful. Great. Good. Okay, we'll go on. So now we're going to have a look at our first equation for our radioactive decay. And it's a relationship between activity and the number atoms n. And in fact, the relationship is a very simple relationship. We have activity is proportional to the number of atoms. So A is proportional to n. And activity is always decreasing. So you remember we said this last time. When you have something radioactive, it's not radioactive forever. So after some time passes, it's less active. So what is really key here is the formula. So this is what the formula would look like. A equals minus lambda times n. And minus lambda is some constant. So really, make sure you've got this highlighted in your notes. Lambda is the constant, and the name of this, you should write down its name. We'll use it a lot. It's called the decay constant. So you can just write down the formula and make sure you have the name of this lambda beside it, decay constant. And the minus is important in the formula because the minus tells us that the A is getting smaller. Okay? So here's your first question for you to do for me. I'll give you the answer in like 30 seconds. It shouldn't take you too long. I want to know what the units are of lambda. So you need to use this formula here to tell you the unit. What's the units for A? And N? Nothing really. Number of atoms, not really a unit. So just should only take you a few seconds actually. Give me the units for lambda. I'll write it down, just to double check. And I'll do it here for you. Okay, so the units are, I think you just said it, yes. What's the units? Well, let's have a look here. I don't really care about the minus for the units. I just really care about what I put in. So the units of n would be the units of, oh sorry, not n, I meant to say lambda. Of lambda will be the units we use for A over the units we use for n. Okay, and what units do we use for A, did you say? BQ. And for n is the number of atoms, I'll just write in here. But what is 1BQ? What do we mean when we say 1BQ? Yeah, if you forgot, that's okay, you can look back at the definition. What's 1BQ? Yeah, come on, say it again. Yeah, decay of one nucleus per second, or one atom per second. So BQ is the same as what? Atoms per second. Can you see that? So like one BQ is one atom per 1 second. So a BQ is the same as atoms per second. So here I have number of atoms per second over number of atoms. So number of atoms cancels. and I'm just left with 1 over S. In fact, 1 over S is something you've seen before. That's the name of another unit. Do anybody remember? 1 over S. Oh yeah, it's to do with that chapter, yeah. What do we call it? Yeah, what's the name of the unit we use for frequency? Hertz, yeah. So although 1 over S is also called Hertz, we don't actually use that for this chapter. We keep it as 1 over S, even though it is still Hertz. Okay. So here's another little one for you to try. I have 1 mole of atoms, and this mole is destroyed. It turns into alpha, beta, and gamma radiation. What is the activity of this sample? And I didn't write it down here. I need to give you the decay constant as well, so I'll just tell you what it is. So the decay constant, you can just use 0.1, will do. So lambda equals 0.1. I would like you to tell me the A, and I give you the N. What's what? What is what number? Lambda 0.1. Yeah. And the N, what's the N here? 1 what? Mole. And how much is a mole? Yes, that's it, yeah. So I'll give you a minute. Give me the activity. Yeah, okay. You have it too? Yeah. So the formula is minus lambda n, which is minus 0.1 times 6.02 times 10 to the 23, which is minus 6.02 times 10 to the 22 BQ. That's what you got as well? Yeah, good, okay. Okay, so here's another one for you to practice. I have a sample of 10 to the 10 atoms, and 1,000 atoms are destroyed per second. What is the decay constant, the lambda? So it's similar to the last question. This time I want the decay constant. You have an answer, Drew? Yeah. Abraham? You have an answer? Yeah. And Louise, you nearly have an answer? Yes, okay. So, what is the n here? 10 to the 10. What else do we know? We know the A, don't we? It's 1,000. That's 10 power 3. Yeah. And we want the lambda, so we can use our formula again. A equals minus lambda, so that means lambda is minus A over n. which means that lambda will be equal to 10 to the 3 over 10 to the 10. I have that the right way around, don't I? Yes, okay. Which is 10 to the minus 7. 1 over seconds. You got the same? Yeah, great. Alright, so this one here, a little bit tricky. I want you to define activity A. But really what I want you to tell me is the definition of activity using things like dy dx. And what I mean by this, I'll give you an example, is for example, force is the rate of change of momentum. So what would that be as a derivative? D what over d what? Yeah? No? Half right. Say again? No.
dt over dt.
That's it, yeah. So rate of change of momentum is dp dt. So I'll give you a minute, try and give me the activity, but in this form, with a derivative, a d on the top and the bottom. Now I will help you by saying, if you look at the original definition of activity, you might get a good idea from that on what to say. So look at your definition and then tell me what the answer is if you think you have it. Lots of thinking. You think you have it, Phil? No. Nice try, though. No? Yes. You got it. Good job. So if you go back to the definition, what's the definition of activity? It was, yeah? Yeah, that's it. And so 1BQ is 1 atom per second. So if you look closely at the units, number of atoms per second. What letter represents number of atoms? N. And seconds is time. So in fact, activity is the rate of change of the number of atoms per time. dN dt. That's another way of defining activity. Okay, so you can just write A equals dN dt. You got that? Yeah? So if we want to find N or A at some time, we can use the equation I gave you a moment ago, A equals minus lambda N. But the problem with this equation is it doesn't have time in it. If you look at this equation here, A equals minus lambda N, there's no time in it, is there? There's no time. There's just A and there's just N. But, yeah, it is time, yeah. And also, another way to get time in is if you look at your last result, what does A equal? Yeah, dn over dt. If you put that in here, you get dn dt equals minus lambda n. Where have you seen something like this before? You've seen this somewhere before. Yep, what chapter? ODE. What's the last letter? E, yes, ODE. Remember this in math class? So what I want you to do for me now is I want you to solve this ODE. Yep. Easy peasy, I know. Since you just did a maths project on it. So see how quick you can do it. And if you want, you can say n equals n0 when t equals 0. You forgot something. Right? Oh, there you go. Now you fix it. Yeah? Yes? So far so good? It's not working for you. You need to take this down here. dn over n equals minus lambda et, and then you integrate. You fixed it? Yes, and in fact you can find this here using the information I gave you. N is n0 when t is 0. Almost. There's something to define as well. Let's see. You use a here for the constant, but because we already use a, maybe we should use a different letter. Call it b. B. So where does the minus go? What, is there a minus here? The minus should go over here on both of these. So that means there's a minus up here. There's no minus here. And now you find the b. You can use that. So far so good. And integrate. You know what this one is, yeah? What's 1 over x integrated? 1 over x. 1 over x? No? No? Write down here 1 over x. And then integrate. Integrate 1 over x here. dx. What does this equal? Do you remember this rule? Yep. For that? Yeah. Equals log x. Yes? I have no problem. You also forgot this one, yes? Yeah, it's what? Huh? N. Yeah. I'll do it on the board now. You all have the right idea. Okay. dn dt equals minus lambda n. dn over n equals minus lambda dt. You all have that. Good job. And then you all integrate it. So Louise, what's this one here on the left? What does this become? You remember this?
Which one?
Yep, this one here. What's this? What will that be? It's like this one. 1 over x dx. Yep. Yes, it is. Very good. And Ibrahim, what do I get here? Yeah? 1 What do I get? 1t? Yeah. And there's a lambda here. So in total? Lambda t. Yeah. So this will be minus lambda t plus c. Now, I put an e on both sides. So e goes here and an e goes here. So now I get n equals e minus lambda t plus c. So I get n equals e minus lambda t. And who? This EC here, I can rewrite it as what? Well, before that, at some constant b. I don't want to use constant a, why not? I'm already using it for activity, so I'll just call it b. Okay, Louise, do you remember how I can find the constant? What do I need to do to find the constant? Yeah? Use what, yeah? That's what we did in the math assignment, yeah. For this one, we use this information here. Yeah, this is like our data. Yeah. So, we have n0 equals b e power 0. So who? As you were saying, b is n0. So now we have our result. n equals n0 e minus lambda t. This is a very important result. This result is in the formula book as well, and you will, there will be a good chance that you will get this in the exam. Okay, so this is very important. They will not ask you for the proofs, which you just did, okay? So no proofs in the exam, just the result here. Okay. Can I change the slides? Yeah. You can do something similar with the activity as well, and basically get almost the same formula. So these two formulas are what you need. N is n0, e minus lambda t, and a is a0, e minus lambda t. Make sure you have them clearly written down. They're very important. Got them? Yeah. Okay. Okay, so I will do this question for you, and then I'll let you try one like this, and then that will be it for that. So I just need you to write down the information in the question here. So the iodine 134, its mass is 268 grams, so if you can just write down mass is 268. The molar mass is 134 grams. And the activity A at the beginning is 1.32 times 10 to the 20 BQ. What letter do you think we use for the activity at the start? A0, yeah. So A0 is 1.32 times 10 to the 20. Now the first question is actually quite short. Maybe you can tell me the answer by looking at it. How many moles are there of iodine?
2 moles.
2 moles. Very good. Why 2 moles?
1 mole is 134.
Yes.
Grams.
Yes, grams, yeah. And how much do we have? 268, yeah. Okay, so therefore, how many atoms are in this sample? If there are 2 moles, how many atoms are there?
12.
Yeah, 2 times 6 times 10 to the 23. So let's write this down. So can you just give me back the information I gave you? What did I tell you in the question? I gave you mass first, yeah. What is it? Yeah, and then the activity at the start was? BQ. And I also gave you the molar mass. So the first answer, how many moles? 2. Second, the N0, the number of atoms at the start, 2 moles, which is 2 times 6.02 times 10 to the 23. This is 12.04 times 10 to the 23 atoms. Okay, part C. What am I asking you in part C? What is the decay constant? So in part C, I'm asking you for the lambda. What formula should I use to find the lambda? A equals, minus lambda n. Lambda equals minus A over n. So that would be, A is 1.32 times 10 to the 20 over 12.04 times 10 to the 23. Now I need a calculator here. You have, so maybe Ibrahim, you can give us the answer. .09 10 to the minus 4. Yep. Now we just need to be careful here with the signs. I know here I have a minus, and here I don't have my minus written in. Sometimes people don't bother writing minus in because they would say something like, we lose 5 atoms per second. It's a bit like deceleration. You know, you don't always write the minus in. It depends how you're using the English. So if I said the deceleration is 5, what does A equal? Minus 5. So don't worry too much about the minus. The most important thing with the signs is this. When you look at the E, the power here should be a minus. What does a minus power in the E make? Will the graph increase or decrease? What will it? Decrease. Is that what you want? Definitely. So don't worry too much about the signs until you're doing the graphs and the powers. Part D. How many iodine atoms are in the sample after 1 hour? Okay. So we used the formula which you just proved. n equals n0 e minus lambda t. So we want to be careful about the powers here, the signs here. The n0 was 12.04, was it? Yeah. Times 10 to the 23. And the e power, the lambda was minus 1.09 times 10 to the minus 4. And what's the t? How much time has passed? Yeah, sorry, I'll go back to the question. I want to know how many atoms of iodine are there after 1 hour. 3,600 seconds, yeah. This should remind you of what from maths class? Where did you see this in maths class? Problems like this. Yeah, which semester? Yeah. Do you remember when we did exponential in semester 1? We did problems like this. Okay, so calculator time, can you tell me what you get here? So after 1 hour, how many atoms do I have of iodine? What did you get?
Big number.
Oh, it should be a big number still. Yeah, what'd you get?
8.13.
10 power?
2.
Yes. Okay. You have that written down? Wasn't even close to the lesson plan. Yeah.
Thank you.
Next part. What is the activity after 1 hour? So which formula do we use for that one?
Can we use?
Yeah?
Can we?
Yeah?
A equals lambda.
Good. In fact, for this next part, you have 2 you can use. Can you see? You can use A equals lambda n because we know the n, or you can use, minus, A equals A0 e minus lambda t. Which would you like to use? Why not? Easier. So can you multiply that n by the lambda and tell me what you get? So the A would equal minus, although we don't need the minus if we're saying it's a loss. Lambda 1.09 times 10 to the minus 4, and n 8.13 times 10 to the 23. What do we get?
I would get 8.9.
8.91
And times 19.
19?
Yeah.
BQ. Now you can say that this is a loss, or you can put in as a minus like this. And a change. So it's a bit like saying, you can say that the deceleration is 8, or the acceleration is minus 8. You know, so don't worry too much about the minus here. It's not really a big concern for me right now.
So what is it?
Oh no, I'm just saying both are fine. Okay? Yep. Next. How long until you have 100 grams of iodine. So how many grams do you have at the start? 268. Okay, so what I want to do first is change 100 grams into atoms. So how many moles is this? What did I say 1 mole was? 134, wasn't it?
Yeah.
So 100 over 134 moles. What's that? 0.... moles. Yes?
Yeah.
So how many atoms is that? This number multiplies 6.02. What do you get?
9 atoms.
Many atoms.
Four
4.49 times 10 to the 23 atoms. You see? So we would like to know how long until we have this many atoms. This is exactly like what you did in semester 1 maths. We need to use this formula. N equals N0 E minus lambda T. Okay, what's the N here? 4.49 times 10 to the 23. What's the N0? 12.04 times 10 to the 23. What's the lambda?
minus 1.096 times 10 to the power of minus 4.
And here we want the time. So I can cancel. That's gone, and that's gone. And I can bring this down here. So can you tell me what this is on the left? Equals E minus 1.096 times 10 to the minus 4t. What do I do next? You know the story. What do I do next? Log. Both sides, yeah. So who, again please, what's log of 0.373? Oh, I know this, yep. 0.985. Okay. Equals minus 1.096 times 10 to the minus 4t. So t equals 1.096 times 10 to the minus 4 over 0.9856, and we get I'm glad Emer didn't see that. Would have been so embarrassing. Minus 0.9856 over 1.096 times 10 to the minus 4, and we get
8,994.
That's enough. So can you tell me how many hours this is? How many hours? So these are seconds.
2.5 hours.
2.5 hours. Okay. Can I go to the next part? No. Okay. Yes. And finally, how long until the sample is 1/4 as active than it was initially? So how long until the activity is 1/4 the initial activity? Okay. So you have A equals A0 E minus lambda T this time. Now, what does the A here equal? What do I say it equals? A quarter. A quarter of what? Initial. So in fact, on the left, this is 1/4 A0. Now does that make sense? Because I say it's a quarter of the initial. A0 E minus lambda T. Now these cancel. What is lambda, please? 1.096. Minus 4. Okay. You know the story. Log, cancel, log 0.25 equals minus 1.096 times 10 to the minus 4t. It's a minus number. What do I get on the left?
Minus 1.39
minus 1.096 times 10 to the minus 4t. So the t equals 1.39 over 1.096 times 10 to the minus 4, which is a large number. What is it? 12,600 seconds. So how many hours? So we have 3 hours. 3.5 hours.
In exam, I write 3.5 hours. Okay?
That's how you should write it. Yeah. I shouldn't write it like this. In fact, you could write it as seconds. I only change it to hours so we can imagine how long it takes. You know, the decay is very different for different materials. So for something like iodine, it can decay very quickly. This is actually pretty quick. Some materials take millions of years to decay. Thousands of years. Yeah. Iodine. Some iodine decays quickly and some iodine decays slowly. This iodine here, iodine 134, that decays pretty quickly. Pretty quick. I mean, after about, I'd say, 24 hours, all the iodine should be gone. There should be no iodine left. It should have changed into something else, not radioactive. So iodine, you know, it's pretty quick, 1 day, and then all the radioactivity is stopped after a day. Something like uranium, a long time, like tens of thousands of years, long time. And then some things too can decay in just seconds. So it's really as short or as long as you like. Okay. Now it's your turn. So I have some questions here for you to practice, and I think you should try them now. Since homework is a little bit difficult right now, with so much going on. After the maths lab report, what other assignments do you have to do?
Chemistry essay and EAP.
When is that required?
I don't know.
Tomorrow.
Tomorrow? For what?
For EAP.
Oh, and then chemistry?
I don't know.
In July.
Oh, it's a long time away. Okay. So you will probably do your EAP essay tonight. Have you started this?
I finished.
You finished this? Don't believe you.
It's more just draft, like a draft.
Oh, it's only a draft. Ah, okay, alright. Well, why don't you spend a few minutes doing this, and then we can see how you do. If you find this easy and get it done quickly, we can go to a new topic. If this is a problem, then I can do more examples on the board. This topic is really important for the exam because it's very common and it's not too difficult. So for the exam, it's a good question. Alright, try these for a few minutes. Okay, so you need a little help with 1D. What do I ask you in 1D? What do I want? How long? So I want time. Yeah. And what do I give you? N equals 10 power 21. So which formula should you use? What do you think? I think this formula. N, yes? 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 Minus lambda 2. Yeah. This is 1021. What's M0? Okay? And what's lambda? You got it. 0.1. T. Yeah? Okay. Alright, so we divide here, that is, I think you had trouble with this one, Abraham, as well, was it? Yeah, so this is 10 minus 3 equals E minus 0.1 T. I can stop?
Use the log.
Use the log, yeah? Yeah. Will I continue or stop? Okay, stop.
Thank you.
No problem. It's like math class. You finished too? Are they right?
I'm not sure. The question 2 is more difficult than question 1.
Of course. I made it like that on purpose. And it gets more difficult. A, B, C, D.
Yeah. It's longer. Decay is longer.
Yes. Sodium 24, I think will take a few days, maybe? I don't know. What's the, what did you get for part D? For 10%?
Nearly 1 day.
Yeah, okay. So after maybe 2 or 3 days, it's all gone. Now there's actually only 2 or 3 minutes left. So before we finish, maybe you can just write these questions down. I will try to upload this tonight, but my wife's parents are staying with us from America, so I might be busy doing stuff. They're visiting from South Carolina. You know this part of the States? South Carolina is in the south, very hot, like a desert. Yeah. So they've come to visit, so I might be too busy to upload it, so try to write it down now, okay?